We are not talking about registers today, so everyone's going to do a little dance of joy. We're going to run around and do something completely different.
Yep. So we're going to talk about housings and enclosures, stuff to put your electronics in, basically. So what happened to registers? Don't worry, you're not done with them, although we're probably done with them for the first half of the semester, pre-spring break. So we like to spiral around. We mentioned that in the first lecture. You know, we go through everything. We've done firmware programming. We've done electronics. This is our somewhat pitiful attempt at doing like design and mechanical design and how you fabricate things.
So if you're an industrial design major or something,
you know more than us.
And you'll sort of understand how the electrical engineer majors feel about all the programming and register lectures.
Yep.
So everyone gets to suffer equally in this class.
But most importantly, the reason we're doing this lecture now is because it's very useful to think while you're laying out your gadget circuit board, which you'll be doing probably towards the end of the week and next week, what kind of enclosure you want to put it in. So all of your gadgets are going to have an enclosure of some sort. That's a requirement. We don't care too much what you make it out of. We're trying to be neutral with respect to that. Not everybody has random machines to make stuff. But when you're laying out your circuit board, you may want to think about, like, where should I put these buttons? Which things should be on the circuit board and which things should be off the circuit board attached to some enclosure so that so that you have a good user interface, basically. Okay, so we're going to do a quick demonstration of 3D printing right now, and then we're going to do a lecture because I'm actually going to design a part and then print it, but printing a part with a 3D printer takes anywhere from 15 minutes to an hour, so kind of have to do that right now in order for this part to be done before the lecture is done. All right.
And this may or may not fail horribly. Spectacular.
So this is a solid doodle. It's a very, very budget 3D printer, which means it's about $500, $600. It's mine. And I'm going to design a part in SketchUp, which is a free tool for making parts. And this used to be owned by Google, now it's owned by Trimble, I guess. And I'm going to make an LED diffuser cap for the LED on your mini gadget because it's horrendously bright. You probably noticed. So the first thing I'm going to do is draw a square. And I'm going to make my square about, let's see, once it's square, I'm going to make it about 10 millimeters by 10 millimeters. So 1 centimeter, which is clearly very small. I'm going to make it roughly maybe 8 millimeters high. So I can type.
So Tom's typing things way in his tiny box down here.
Yeah.
So
I don't
psychically
see that.
summoning the box.
Right. I'm going to make another square in the center that's actually that's pretty good, 6.4 millimeters by 6.4 millimeters. So if you look at the data sheet for the LED, it's 5.5 millimeters wide, and it's a square. So I'm making a little cap, and I want it to fit over it, so I'm making that void bigger than the square. Now, it may not fit over it at all because 3D printers, especially budget ones, don't do very small features very well, but whatever, we'll give it a try. The nice thing about a 3D printer is if it fails, you just, change it a little bit and try again. Okay, so I did that. That's roughly centered. I'm going to call that good enough. And now I'm going to make it about 3 millimeters deep. And there's my part. Yay, just made a part.
So you guys can all go download SketchUp. It's a pretty free tool. I think there's a pro version of it, and design parts like this. Basically, SketchUp works by draw a shape and then push or pull into and out of it. So you just saw Tom took a square, then pulled it up to make a 3D shape. Then he drew another square and pushed it in to cut out a 3D shape. And that's how SketchUp does everything. There's a couple of other 3D tools. Some of you have heard of SolidWorks. SolidWorks is installed on all the cluster machines. That's a much more powerful tool.
Yes.
And instead of using this idea of pushing and pulling shapes, it has this idea of constraints. So instead of you saying, I want to push this in, you apply some constraint to it that says this is going to be a thing that's 2.4 millimeters from this other thing.
Yeah.
And SolidWorks figures out how to make it like that. It's much more complicated though. So if you want to do that, there are tutorials in SolidWorks for doing that, for if you're getting really serious about this. If you are just interested in making like little boxes and simple stuff, SketchUp is a lot easier and a lot freer. So
SolidWorks, I think you can buy a student edition for $100.
yeah, it's available at the computing store. You can get a 1-year license,
Yeah.
student's edition for $100. If you're planning on getting very serious, if you're into mechanical design, I would
You should
highly
get
recommend
SolidWorks.
it. If you're not into mechanical design, you just want to make like cool sketches of the things you're working on, SketchUp will be so much easier for you. Because it's relative.
And there's a lot of video tutorials. We're not going to get into how to use SketchUp, but there are plenty of video tutorials that talk about these.
And both of these are able to create parts that you can send off to a 3D printer.
Okay, so I'm going to do that now. So I have to install a plugin in order to export to the right kind of file type. So I'm going to export to an STL, and I'll do the entire model. And I was using millimeters, so exporting as millimeters. And I want an option to be STL.
STL used to be for stereolithography. That's why it's called an STL file. But what it basically is it's 2D layers. It slices, so it just goes up, 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 up. So these birds, triangles.
It's triangles, it's a mesh.
So it's a mesh triangle representation. But basically the 3D printer people have all co-opted it as sort of their thing of choice.
Now, low-end 3D printers tend to use open source software. They don't come prepackaged with any specific software. So I'm using this specific software. It's called Repetier because it's German, not French. And it allows me to set things like, so a 3D printer has something called a print bed, which is where the prints go. And you want to heat that usually to about 90 Celsius. It also has an extruder, or this kind of printer does. So there's this big roll of plastic in the back. It looks like weed whacker wire. It goes into this hot end here. And once that's hot enough, which is about 200 Celsius, it'll start extruding plastics.
And basically this is a thermos plastic that you can bring up to its melting temperature, extrude, and then cool it down again, and it stays the same kind of plastic. Other kinds of plastic just melt and burn and become a horrible mess. So you can think of that as basically there's a robot glue gun that's just driving around, extruding stuff, and then the entire print bed will just move down a 1/10 of a millimeter or something, and it will do it all over again. So it's doing it all in these layers, and just going down and down and down, making this layered object, which is why you'll see a lot of things saying slices and slicer. And basically, it just figures out what each slice looks like. And if you're lucky, the machine, each sliced layer will stick to the bottom layer, and you end up with your part. Sometimes when the machine is angry or feisty, you end up with just spaghetti, because it doesn't stick, and you just end up with this plastic spaghetti just filling your machine.
You might get that, or sometimes, so it's using 3 stepper motors to move in the X, Y, and Z directions. And sometimes you have something called a misstep, where your print will suddenly move over because it doesn't actually have an absolute position reference. It's just telling it to go so many steps.
This
If
one
the
does.
motor, yeah, if the motor gets stuck for some reason for a second, your part is basically useless. So there's a lot of.
The advantage of these printers is that the raw material, this plastic, is reasonably cheap. And so you can just sort of keep printing and it's, a couple of tens of bucks of material. In fancier printers, that material is much more expensive. It can be like $300 per
Kilogram.
quarter kilogram or.
Yeah, so Larry Hagers runs the Collaborative Machining Center, aka the Chemistry Machine Shop in Doherty. He has an object 3D printer that the biology department purchased, which does amazing print jobs. Like you could basically print screws and then screw them in. Like it's that fine resolution. The only detail that they always gloss over is that the photoactive resin dust they use is like $300 a kilogram. So you say, well, for $300 a kilogram, I'll just go buy some screws. And I'll print them out of plastic.
Okay, so I've just homed it, which means I've put the print head in its home position and the print and the hot, and also now I'm going to add the object that I made. So that was LED mount 2. So I just added it. There it is. It's pretty
Now,
small.
can you add another one side?
It's
Yeah,
not a ton.
so I'm gonna add another one as well. Okay.
Yeah.
I guess I'll move one of those. I will try to move one of
Now,
those.
because these things are built up in slices, you end up with things where things are very strong and accurate when they're done in the layer, but the accuracy between layers and the strength between layers is a lot weaker. So if you were gonna build like a crescent, like a wrench, you wanna print it the flat way. Because if you printed it the vertical way with these little slices, as soon as you like flexed it a little, the whole thing would just snap wherever you were flexing it. Whereas if you had the wrench that was printed flat, you'd flex it, but the material was printed this way, it'd bend a little, and you wouldn't be able to do anything with that wrench. So what Tom is doing is he's experimenting with which way is going to be more accurate, which way is going to come out with a better part. Because depending on what you're making, if you're not just making a square or a box, you might have some like say, well, gee, I'm making this rounded thing with this thing on the edge of it that's kind of funky shaped. But this is the only thing that matters to me. So I'm going to put that face down on the bottom so that as it's printing, that's what's going to be accurately done. And then towards the end, the machine starts skipping and missing, gets a little funky out there, and I have to hit it with sandpaper. That's okay.
So yeah, I put in two pieces, or two of the same pieces, but one is sideways to see which one will print better. I'm going to go with, and now I will use this software to slice it. What that means is basically it's going to take the model file and calculate based on a number of settings that I've set up. I've sort of configured the printer to be a certain way, hopefully optimized for printing small parts. And it will create what's called G-code, which is kind of a universal, I guess, universal files the way you have Gerber files for circuit board fabrication. G-code is that for 3D printers. It's a universal file that tells the printer, you go to this point, then you go to this point, then you go to this point at this speed, and you're extruding your plastic at this rate.
I think it's the industrial version of Logo, basically. It came out at the same time in the 80s. Yep.
So I hit slice, and that will slice the file.
If you tried to print it top down, it would probably work, but then you have this unsupported area. So
Yeah, so with this particular printer, this has got a single extruder head. Other fancier printers have actually two extruder heads, and one of them is used to print support material, which is basically either, well, it can be the same sort of plastic, but generally it's printed really finely, it's meant to break away later. So you can do stuff that way if you have an unsupported part, like printing a cup or something, where basically the printer will print this like a really like crappy mesh, and basically it's designed so that afterwards you just snap it on.
So this is what a single layer looks like. This is layer 23. I guess I can go to layer 1 so you kind of see. So this is the beginning. Go to layer 2. So you can pull this.
Yeah, so it's kind of cool because you see it just sort of like forming your part, the voids appear. And usually you double check those if you're really like making stuff with these all the time. Yeah, good
How
question.
do you make sure you don't accidentally print something that could damage the printer?
You're careful.
Yeah.
With this one, you're careful. Basically, you can tell it to print beyond the print bed. The print bed in this one is 6 inches cube. So you can't tell it to go too far, and then there's no real warning for that.
Damage it usually though. Mostly
If you're not watching it and it does it for like an hour,
okay.
it might just have like a giant pile of plastic that's sort of
You don't
stuck
damage
inside.
the machine. The machine is just steppers. It can slip without hurting itself.
Yeah.
And it just extrudes plastic, so you're okay with throwing away plastic spaghetti. Nothing's gonna happen.
Yeah, I've had this like just fail.
How does this printer compare to the one in the Meki shop?
Which one is that?
It's
It's,
probably
Yeah.
Excalibur? What is it?
I don't know. It's really big.
It's really big. It prints this white plastic.
Yeah, do you have to take what it prints and then put it into like a
Yeah.
washing
Yeah.
tub? Yeah, okay, that's a much better printer. That's closer to the object that Larry has. That's using like a photo lithography process for basically, what's it use, a laser or something?
Usually they use some sort of coherent light. A lot of the new ones now use like the DLPs that are in like projectors. They use those to project the image onto the stuff. And then the polymer is this expensive polymer that reacts to light. So if there's lots of bright light, it reacts, hardens up, and then otherwise it just stays liquid. And then they lower the bed, the this fluid.
Yeah, so that makes the actual fluid that you use to print stuff a lot more expensive, but it also means that you have a lot higher accuracy. Because it's much easier to focus a beam of light than to actually basically be squirting this plastic icing all over everything. So that printer would be nicer. And you'll be able to tell the difference between the parts. These parts printed on an extruder like this have like a crisscross pattern. You can see the grain very clearly. Parts that are produced out of a lithography type of printer won't have as clear of a grain, and they'll look like solid plastic. But not like solid.
Another detail is that the stereolithography ones, because they print such thin sheets, it can take 10 to 50 times longer to print parts, because you have to print, if you want to print an object that's 1 inch tall, and you're printing, you know, 1/100th of an inch, it's going to take 100 steps. If you're printing 1,000th of an inch, it's going to take 1,000 steps. Right? These machines can be very slow, especially for large objects. Like 36 hours for a print job is not unheard of.
Yeah. All right, so I'm going to hit run job and hope that everything works out. And it's going to take 34 minutes to print those 2 parts. And there is a piece of plastic sticking out. It'll probably just break off.
Okay, so this is a 3D printer. There are many like it. There are much nicer ones, but this is Tom's.
This is mine.
So basically, don't worry too much about the specific details of like this specific piece of code. Each printer you use is going to be slightly different, and you'll have to just sort of get it. When you go and use a printer, you will learn how to use that particular printer. It'll use slightly different software, and slightly different stuff, but the general process is the same. You're going to create a model file in some sort of CAD software. You're going to probably export it to an STL file format, and then you'll go through some set of steps which let you slice that up and send it to the printer.
Okay.
And then you wait a long time. That part is also guaranteed.
So when we did this class a couple of years ago, we did not have this little interlude, because you couldn't just buy one of these for $500 and throw it on a table and say, hey, let's make a part in 30 seconds and start printing it. I think we spent more time talking about it than actually like doing the actual setup and printing.
All right, so yeah, definitely. Okay, so that'll interrupt whenever it's complete and cold enough to pick up. Okay, so let's talk about housings and do an actual lecture. So there's a bunch of philosophical reasons to build housings. I mean, there's aesthetics. You get to pick the aesthetic, and the aesthetic should sort of suggest through its design what your gadget does. And then there's usability. You know, if somebody wants to pick up and use your gadget, you shouldn't be cruel and just give them a circuit board and be like, here you go, don't shock yourself.
Watch out for those sharp fiberglass edges I didn't really sand, or all these spiky little bits on the bottoms that didn't cut the legs off.
Yeah. Okay, but there's also a number of practical reasons. There's electrostatic discharge, which is basically on the carpet, and then you go zap to your circuit board. That can still happen. It doesn't happen nearly as often as it used to, which is why we don't have you all like wear clips rounded to some metal when you're assembling your circuit boards.
But it's important to remember that like taking the balloon and rubbing it on your head and sticking it to the wall, that's somewhere between 10 and 50,000 volts. Circuit, your little microcontroller likes 5 volts. 50,000 is a lot higher than 5.
Now it's a very low current.
And what ended up happening is in circuit chip manufacturer now, anytime they have those little legs, they now put lots of diodes and protection circuitry so that when 50,000 volts show up, they try to discharge it through these little diodes that, as they got more comfortable with the designs and more complicated designs, they could stick that in everywhere. So it used to be a MOSFET, you'd look at it funny and it would die. And they'd have to do very specific things to put it on your board. And then once on your board, you'd have to protect it in 37 ways to make sure that nothing happened to it. But now, it's all self-protective. So
last year I had this tested at a lab. It's a robot that I sell.
Why don't you tell us about your robot?
Well, it's later.
Okay.
But so I had it tested at a lab to make sure that it was, I guess, for consumer safety reasons, and also radio FCC reasons. But one of the tests was basically a guy with this giant zap gun that just zaps things at 10,000 volts, and he went zap to every exposed metal surface, as pretty much any hole in the enclosure he zapped. And then it was kind of like, well, is it still working? Fortunately, everything still worked. There was like a couple sensor flips, but it still worked. So yeah, so electrostatic discharge is something that they test for. If you just have a bare circuit board, it's really hard to pass the zap test because it'll zap everything. All right, so skin creams or skin oil, they actually can corrode parts on your board if you're really like handling the circuit board a lot. The oils can eventually cause corrosion into solder and copper traces. Obviously, you have to, putting it in an enclosure means you can do this, and it'll probably be okay. So almost every consumer product has to pass through that 4-foot drop test and survive and not break into 1,000 pieces that small children can choke on. That's the world we live in, so it's probably a good thing. But yeah, so housing is one way to prevent stuff from breaking off the circuit board because you've got it nicely in place. Scratches could alter traces or break traces. When you take your X-Acto knife, you scratch it across your circuit board, it's not going to work anymore. And then, you want to protect other people. So you want to protect them from shocks. If you certain circuit boards, like the one on this very cheap 3D printer, get very, very hot, and they put a little plastic plate over it. They still allow, you can still touch it. Usually, you don't want that to be like CPUs in computers can get to 50, 60 Celsius very quickly.
I think 40 Celsius is when you start worrying about burns.
You start noticing it, yeah.
Like the
You
water.
probably don't want your water to be more than, you don't want to take a bath in more than 42, 40 degrees Celsius.
But the thing is, these parts may be designed to operate at 80 degrees Celsius, and that's okay. Like, they're happy, you just have to make sure that heat stays away from people's skin, especially with big motor drivers, power systems. So I don't think any of you have to worry about that. For your gadgets, it's just things to be worried about.
Once again, from the engineering perspective, we talked for probably 3 times as long about why you want housings to, protect your electronics, and we basically barely talked at all about how you want to use housings as a user interface tool. But that's just us. Design students could probably talk about it the other end much better. So, all right, we will talk about it a little. So you want to design the functionality in mind. You want to apply what your gadget does without having somebody read a user manual. So, shape, color, all of those things are important. You can have labels on it. If it looks like an alarm clock and has a clock face, people will be very confused if it's a laser gun or something.
Yeah, and it's, right, there's this thing where we say, oh, I have this electronics, now we put it in a box. Now it's in a box, it's safe and protected. But someone comes and says, okay, I'm going to use your gadget. What does it do? What is that button for? What's that other switch for? You have all these unlabeled things. You're like, I don't know what this thing is. I'm just going to put it away and leave it alone. Whereas it may be something you want someone to use.
I have a great example of this. So when I was at grad school, we found this box. And in this box, we found a smaller box with wires coming out of it. And no one in the lab knew it was from some other project. And you plug it in, and it would output a video feed from a camera somewhere in the box that had a dotted line. And then there was a little LED bar which would start counting down. And then at the bottom, it would just start beeping a lot until you pointed at your face. And then it would stop for a while, and the bar would go up, and we were like, is this some sort of weird face detector? And we were like, how does it work? We couldn't figure it out. Later, we discovered it was actually a prototype for one of the sleep detectors that they use in newer vehicles, where it points at your face and it's actually looking for if your eyes are open or closed or not, right? And it has a timer to figure out if it's not for for amount of time, it'll beep and wake you up, right? But all we could figure out is this is the Noyotron 5000. Put it in front of someone's desk and hide it, and then as long as they're sitting there, it'll work for a while, then it'll start beeping, they'll come back to the desk, it'll stop beeping, and then it's great.
Yeah. And I think the other thing, you really want to avoid suggesting things that it can't do. This is a little outside of gadgetry, but let's say you're building a humanoid robot. When someone sees a humanoid, they say, oh, this must be able to walk like a person, talk like a person. But no, like Asimo doesn't actually say anything, he just sort of sits there and stares at you with his beady, I think they have 2 eyes now. Right, and that kind of bothers people. Whereas if you have a robot with no, and you know, he has arms, but he can only pick up like an empty toilet paper tube. And you know, it's the sort of things where you say, well, you have arms, surely you can do things with them. Whereas a robot with no arms, like you sort of cut it some slack. You say, well, you don't have any arms, I'm not going to expect you to grab anything. If you make this super complicated thing that all it does is turn on and glow softly, people will be like, well, what are all these like motors and arms for? What was the point of this thing? You know, it looks like an unfinished project as opposed to everything you see is exactly what it does. There's no extra weird stuff. It's not trying to like, you know, you don't have it like in this enclosure that looks amazing, but it doesn't actually do anything with all the features.
So, and I guess the last thing is you just want to be explicit with what its functionality is. So, showcase what you want people to get out of it, what the desired functionality is, and stuff that's unimportant, generally you want to hide, like, you know, your ISP port that you guys use to program the gadget, that 2x3, you know, array of pins. You probably don't necessarily want to have that sticking out of your housing because a user is not going to interact with that.
But having said that, you might want to make it easy to get to.
Yes.
We had a lot of people who make these like,
Yeah.
glue their circuit board into these boxes and they're like, oh no, I have to change the code. How do I get in there?
I mean, you guys are still effectively making prototypes, so you're not making like the next iPhone, which is just like impossible to get apart because Apple
Yeah.
likes it that way.
Yeah, so think about little doors or some kind of opening that you can get to for your own sake.
Okay, so there are many ways to design housings. We are totally fine with all of these. You know, if you want to draw something on paper and pencil, it's very easy to do that. You don't have to learn any crazy software. And if you took any sort of drafting class, they probably still cover so that you know, like, okay, what's the rough dimension? You draw it in the right dimension. So you want to express salient features. So that's how big is it in all dimensions? Where are the user interface features? Where am I putting my LED? Where am I putting my screen? Where am I putting my button? That kind of thing. That's true in all of these things. Then there's computer-aided design software. So we talked about SolidWorks. Just showed you SketchUp. You can create an exact model. You can even model your circuit board so that you know, so that you think of it as a part within this bigger model that is your entire gadget. So you could make like a housing, and you would also put your circuit board in there as a 3D model. I think there's ways to export from Eagle. You can export like 2D shapes pretty easily. So you can export the shape that is your board outline pretty easily. But unlike some of the more expensive printed circuit board design software, you can't just export like a 3D model of your circuit board. Whereas some of the other ones will actually model, like have native models of all the parts.
You have to make all the models, but yeah.
Okay.
And the nice reason to do that is if you're doing this 3D stuff, you say, well, here's my circuit board, I'm going to put it in there, and then you say, here's where I'm going to put the mounting bolts. And now you have mounting bolts, you put the LEDs in there, you say, okay, the LEDs are on the right side of the board, facing that way. I'm going to put the programming port over here on the bottom. It helps make a lot more sense, because this really is like a 3D construction process, and it can be hard to do when all you have is like this 2D model in Eagle, and you say, well, I've got this box with stuff everywhere, what's actually going on here? And so if you want to start from the model instead and say, okay, I'm going to make this thing, it's going to look like this. I like how this looks now, let me figure out what the circuit board's going to cram inside of it, how it's going to look. Right, so maybe start from what you're used to and go to the circuit board.
Okay, so just example software again, there's a whole lot. I mean, AutoCAD, IronCAD, SolidWorks.
And as students, you guys have access to a lot of these,
Yeah.
whereas like SolidWorks is like a $5,000 a seat license.
Yeah, once you're not at the university,
10,000
all
maybe.
these are ridiculously expensive.
Except for SketchUp.
SketchUp
It's very
is
simple.
annoying.
Yes.
If you want to do anything.
Yeah, I can't do SketchUp.
All right, so just to drive this home, I've got 2 case studies. So I have a small robotics company that makes these 2 products. This is the Finch robot. This is a Greenlink robot controller. I'm going to pass these around, I guess. And the housings were fortunately not designed by me because they would look like boxes. They were designed by somebody, industrial design consultant. So the Finch is a low-cost robot for computer science education. It's USB tethered. It has a number of sensors, and it also can drive around and has a full color LED in the beak and a buzzer. So the idea with it is basically it's a computer peripheral that is interesting to programming for, like a mouse that can drive itself around. So it's used primarily in middle and high school, and also some introductory college, community college, career college courses. So when you think about like how this affects the circuit board, you know, some of the sensors on the Finch need to be exposed, like light sensors or obstacle sensors. The full color LED needs to be in a nice place, and it should diffuse well so that the colors are interesting to look at and not like separate too much. And then obviously you want to protect your internal circuitry. And then most importantly, you know, because it's a product, it should have some sort of appeal to students. So you want to think about aesthetics. So sensor placement, you know, these are IR LEDs, so they need to stick out of the housings. This is a light sensor, you're probably familiar with it. Here's a temperature sensor, and this is an IR detector. All of those need to be exposed in some way. And if you look at it, you know, the exposure is there, but the way that the housing is designed, it's not just randomly exposing these, it's making them look a little bit like eyes, giving them something of like a feel of a, you know, a finch or a bird. So here's where they actually are. We also have an accelerometer, but that doesn't need to be exposed, so it doesn't matter. But the key about an accelerometer is it's really cool for detecting orientation, right? So you probably want to make this into an input device. So it's actually designed with the idea that you would hold it with 2 hands and use it almost like a game control. So like you can cover up the light sensors, use them as buttons, and then you can orient it and basically program games using the robot. Protecting the PCB, this was fun to do. So consumer products. Need to survive 4-foot drop tests. They don't need to keep going. They are allowed to break, they're just not allowed to break into thousands of pieces. But, you know, given the environment, which is going to be like a bunch of high school students using this, if it broke the first time it dropped, a lot of teachers would be angry with me. So it needs to be able to survive that kind of. Oh, that's me, like using the cable. A lot of the times it just flips onto its back. That's okay though, as long as it keeps going. So in terms of aesthetics, we actually, the way that we designed the mold is the industrial designer came up with 9 different shapes, 9 different like ways of enclosing the circuit board. And then we presented those drawings to about 100 high school computer science students. And I think these 2 were like the top 2 designs. And then we sort of merged those. Because as a designer, you still have, you know, you don't have to blindly follow what people say. You don't have to just pick the winner or whatever. But you use that feedback in your design process. Another cup, yeah, I mentioned the 2-handed grip. It also stands on its tail because a lot of the times when you're testing a robot, you want to put it on blocks to, you know, watch your program run without actually having it do something crazy on the floor. So this just stands on its tail testing. So just little things like that, the housing can really improve the user interface, I guess. The BrainLink is basically mind control of toy robots. If you've ever used a universal remote control, it's basically that. You can capture infrared signals and then replay them. And a lot of the robot toys, like well, Roomba's a vacuum cleaner, but Roombas, Robo Sapiens, a lot of those kinds of toys have just infrared remotes. So this is like infrared remote with a Bluetooth connection to your computer, and then you write programs to make your robot puppet around and do stuff. So instead of just having a little Robo Sapien that like you control with the remote control, now you've written the programs to control it. So it's running on your computer. It also adds a little functionality as an accelerometer and a buzzer and a light sensor. And a full color LED, because I've got those on. And you can add sensors and stuff. So here the housing is, you know, we're not expecting people to be picking up the housing too much, like picking up the gap too much. It should be stuck to a robot. But the question is, what's the right size? Like if you've looked at toy robots, they have all these different morphologies. So the person who did the industrial design made a bunch of stuff out of foam and tried to stick that to robots. And it was kind of like, how do you stick it to like that and that and that? And came up with, you know, here's some early design, and then eventually sort of picked this one because it seemed like it fit on the most different types of robot shells, this sort of tripod design. So there's the first prototype. And then that greatly impacted the electronics because, you know, it was a tripod shape, so I made a triangular circuit board, and it had to be pretty small, so this thing was very dense. It was at the limit of what you can do with a two-layer board. Yeah.
But still,
If
almost all of his parts are on the top side of the board,
Yeah.
which is another cost. When you're doing automated assembly, like what you guys did with Mini Gadget, if all your parts are pretty much all on the same side, then you go through the machine once and you're done, as opposed to someone having to then put parts on the other side and doing it all over again, which doubles the assembly cost.
Yeah, and then in terms of assembly, like you have to attach it, so there's screw holes, you know, to bolt it into the housing, and then you have to bolt the two housing pieces together as well.
And they're not in the most convenient places,
No.
but they're where it worked for, you know, the back and forth between the shell and the
Right.
circuit board design.
And there's this little battery in there too, because it has a little lithium polymer battery. So here's how it fits on different things. Velcro dots are fine, like, you know, you put like a Velcro dot on each of the three lights, and that all works. Okay, so constructing housing. So this is all of the different ways of manufacturing things, of which 3D printing is one, which is really cool right now because like
It's gotten a lot
new.
easier.
It's gotten a lot easier, but it's just one way. So we're going to talk about all the ways. So start with how people have been making stuff for centuries, basically, and that's traditional machining.
Yeah, it's,
I guess for 1 century.
yeah, I think, you know, this whole replacement parts revolution, it wasn't until probably the Henry Ford, like the automobile, like they had truly replaceable parts, some rifles, whereas like a Singer sewing machine, those were cranked out in the tens of thousands in the very late 19th century, but they still were, they made you a couple extra needles and they kept them in a box or like little parts for the machine. And so when you mailed them, you know, a postcard saying, you know, hello, I have broken my sewing machine foot, please mail me a replacement. They kept one for your serial number and could replicate it and then send you another one. So they were all still very different.
So this concept may be a little hard to understand because of the world we live in.
Yeah.
If you had 2 identical items or 2 identical products and tried to take them both apart and then rearrange the parts, they just did not work. They didn't fit because they didn't have machines that could make parts at the right tolerances in order to do that. Every single thing that was made until the late 19th century was unique.
Like every screw was different.
Yes.
Like they would make the screw, then they drill a little hole and screw the screw in. Your thing had 5 screws, those 5 screws could not go in different spots.
So then somebody came up with replaceable parts and people tried to figure out how to make machines that were really precise. And then they were able to do things like machine 1/4-inch drill bits that were actually 1/4-inch and make identical screws, crazy stuff like that. So a machinist can make almost anything. Basically, there's a machine for it and there's somebody who has a bunch.
And
There's
you can
several
make-
machine shops on campus.
You may have access to them, you probably don't, because CMU doesn't like people making things.
Pretty much any material, if you want to do plastics, you usually have to, in this process, you have to make molds out of metal and then plastics. And then, yeah, there's cost. Basically, they charge you for the machinist time, which it's a highly trained person, so it costs money. And then materials, which can be very cheap or very expensive.
And then we're not going to get into the sort of endless possibilities of design, but depending on how you design something, you could make something that could be cut with a laser cutter, and then you're paying for 5 cents a second for someone to laser cut something. And if you have a very small thing, it might cost you $1.80 plus 50 cents for the plastic. Or you have this thing that's slightly three-dimensional, and then it needs to be molded, and then it may cost you $10,000 to make that first mold, and then 22 cents per piece. But if you only need one, you'd say, well, maybe I don't actually want to do it that way. So these very minor changes can change how manufacturing is. So normally you consider manufacturing practices when you're designing something and you really understand the machines you're using. 3D printers, if you've been following them, they've been sort of touted as this revolutionary new thing, and the reason for that is you just sort of make a 3D object and then you print that 3D object. You're sort of skipping the whole CAM step, which is the computer-aided manufacturing step, where you figure out, okay, I've got my machine, how is it going to drive around and cut out every little profile? Because if you were going to use a milling machine to cut this out of solid plastic, you'd have to figure out all the cuts, how you're holding the material down while you're cutting it with this huge head. Whereas here, he's just printed something. He didn't think about any of that. He just said, I want to make this 3D object, and then I'm going to print it with the slicer, and the slicer's going to do it.
Yeah.
And maybe it won't be perfect, and maybe it'll tweak it, but like, he skipped basically 90% of the effort in designing and manufacturing something, which is figuring out machines and machine paths that will make your part. And now these things are $500. They used to just be $50,000. So lots of people have been using these for 10, 15 years, but
Not always in like well-funded labs, or well-funded machine
So like
shops with a technician.
GE would print out engines out of plastic and see if all parts fit. Say, okay, or let's increase the clearances here, or this cam doesn't work quite right. But that was a very expensive machine they were using.
So some of the machines in this kind of machine shop.
Yeah. So lathes. We're just gonna basically lathes just spin something and then you can cut it. This is how you make screws. This is actually how you build a mill. And then with a mill is basically just it's basically a drill press that has an XY table and it can handle side loads. So then you start cutting things out by moving the part and leaving the table fixed. So then you can make a nicer lathe using your mill, and then using that nicer lathe, you can make a nicer mill. So that's really what they were up to in like the 1850s to 1920s, is making newer machines. Water jet and wire EDM are sort of different technology. A water jet is basically a laser cutter also fits in, where you're cutting a 2D material, and a water jet basically just uses ridiculously high pressure water with a little bit of grit, and it's such high pressure that it cuts through steel, it cuts through aluminum, it cuts through plastic, it cuts through people, it cuts through everything. It's just this incredibly high power water jet, right? So it's very obvious what it's called. Wire EDM, electro deformation. I'd have to look it up, but basically wire EDM is different. They basically have a little wire and then they inject, I don't know, as much current as they can to basically vaporize your material. And so if you're building something out of metal, you can basically cut and vaporize everything. So it's very similar to a plasma cutter in terms of what it can do. It just vaporizes your metal, and if you care about it, it doesn't cause any machining stress. So you can basically throw a plate down, cut it, and you didn't have to like fixture this plate for these huge cuts, which is why it was nice. Brakes, benders, and English wheels, those are sort of manual devices for like bending sheets of metal and doing cool curves. Stamps and presses, you make dies. So like, right, a simple stamp would be like, letters, and you could just hammer a bunch of letters into your thing and have like serial numbers. But you could also have crazy shapes and like stamp out little spring contacts or stamp out little contraptions. Then there's molds, or you can skip the molds and do 3D printing.
Right, so plastic injection molding is how most plastics you interact with are made. Basically, somebody takes a design, or designs a mold, or designs a piece, I should say, and then somebody takes a mill and makes a reverse impression of that mill in steel or aluminum, and then basically they clamp it down and they shoot plastic into that reverse impression mold, and then they extract it, and you get a piece of plastic that looks like the top pitch shell.
And there's details. If you've
That's
ever
with
made
injection molding.
a model from a kit, you'll notice they come in these weird like sheets with like all the parts held together with these little things. That's actually what comes from the machine. There's all these extra channels for fluid to come through.
And a mold is extremely expensive and then really cheap in that, you know, for the Finch, I think that top mold was about $5,000, and then each piece is about $1. So they basically clamp it down, they can make it extremely fast, whereas a 3D printer can make a single piece in like an hour. So it's 5 seconds versus an hour, but $10,000
Those,
versus
that shell probably would have taken 15 to 20 hours.
Oh, on the printer?
Yeah.
I'd say 5 hours, based on other things. It depends on the resolution too.
An object,
Yeah. The other interesting thing is you can also make very short-run molds where you print an object using a 3D printer. Then you use like a silicon molding material to make a silicon mold of your object, a resin mold of your 3D printed object, and then you use it with an plastic injection molder.
Which works for
about
a while.
100 pieces.
Yeah, you can make about 100 pieces.
And then the mold itself, because it's just silicone itself, just starts breaking apart.
Yeah, just crumbles. So there are places you can get this stuff. For this class, it's not required, but if you're interested in this stuff, building stuff in general, you kind of want to get to know these people. You want to be able to operate these objects because it really informs you how things are made. And when you know how things are made, then you start to learn how to make things.
So in terms of shops, there's the EC shop, the Collaborative Machining Center, we'll talk about it a little more as well. And then there's Robotics Club actually is a small machine shop, and mechanical engineering obviously is a machine shop.
There are a lot of fiefdoms on
Yeah,
campus.
it's really
Yeah,
a question
don't
of
interrupt
are you a
that.
major?
So these days, it's also pretty common to not do your own manufacturing.
Yeah,
So
so
the
like
last two
e-machine
quotes
shop,
here.
they will just.
Yeah, you design it in someone else. Like if you have a 3D printed STL file, you could simply go online and give someone your STL file, and for a bunch of money, they will print your part and send it to you.
Or
In some
mill your
material.
part, or lathe your part.
Yeah.
They will do any of these things.
Do you have tech shop on here?
Later, but
Okay.
yeah.
That's where we go.
Yeah,
Okay, that's like.
All right, so another thing you can use is a laser cutter, which I think you may have access to a laser cutter depending on which major you are, and department you're in. But it's like a water jet, except it generally only works on plastics, I think.
The really nice
wood.
ones.
Yeah.
Yeah, wood's tricky. You really, so
It's
with,
lasers so it can get hot and then.
so you have to make sure there's a super cheap laser cutter just shoots, and you have to use the right materials. Nicer ones, they have like argon gas or
Yeah.
nitrogen gas hookups so that,
Cool stuff.
well, it just prevents oxygen from being in the area so that when you're doing like balsa wood, it doesn't just combust and go away. Which you can do where you're like, well, I cut out this thing of balsa wood, but all my edges were on fire and they continued going. So the shape I wanted is a little charred from what I.
And that actually happens with certain plastics too. Like this is a very common occurrence.
In fact, if you look at a laser cutter cutting something, you will frequently see a little bit of flame shooting.
Yeah.
And so the nicer laser cutters all use gases to keep that from happening as much.
So, I mean, you get 2D pieces. It's nice in that you design something and it's pretty easy to just get it made. You can just
Yeah.
get sound stuff. And then you can, arrange those 2D pieces into 3D shapes. Usually that's how people do. They make interlocking pieces and you've got yourself a house.
So SCS has one now?
Yeah, the
Yeah,
same.
it's
same
Larry.
characteristics.
Okay, and they're collaborative machines. So this is Larry Hayhurst. He's a nice guy. he has laser cutters, and he sort of is trying to promote this open access shop, so you may be able to talk to him. What?
Oh, one of the two lasers is important.
Uh,
But in any case, the nice thing about laser cutters is that they're very cheap, because essentially, comparatively, they're very cheap to these other methods. Because basically, there's very little setup involved. You put a sheet of material in, you kind of hit print, and it kind of goes. And the other thing is that there's not a lot of manufacturing constraints. So basically, anything which is a 2D file, you can essentially just cut out. Like the laser can just run that path, and they can give you the piece of plastic. Which means that this is also a particularly good thing for you to do online from various places. So I think Palolu has a laser cutting service. There's a number of
Yeah, it's
other
easier
companies.
generally
Yeah.
to cut a piece
so
very cheaply.
also,
Not a lot
like,
of setup costs.
Yeah, so even if you don't have access to one of these machine shops, you could very easily take your drawing, send it to someone online, and for not too much money, they just mail you back the plastic pieces.
It's probably $50 to $100.
Yeah.
and we're talking about drawings, we literally need a drawing. Whereas the 3D printer people stole the stereolithography files, these people have basically stolen TXF, like Corel Draw is used a lot.
There's something even taking.
Where really, if all you're doing is cutting out stuff and not etching, you just have to give them a black line drawing, and the black line is where they cut. And so you could do it in Paint, you could do it in Illustrator, you could do it,
Does that work? You need a raster, you need a vector file.
well, they would raster it,
Or,
they'll happily do it. Like, that's a detail.
but yeah, you can basically.
Like, you could do it in Paint, you could draw it on paper and scan it in.
Now, you may not want to do this, because then when you get your pieces back, it'll be a lot like the 1850s, where none of your pieces will fit together because you scrolled them all on paper. So if you use an actual CAD tool, you can
Yes.
be a lot better about these pieces actually fitting together.
But it's much simpler.
Yeah, at my high school had a laser cutter, and it was just a parallel printer. The way it worked, you could actually just open up Microsoft Word and do Control P.
Yeah.
You
So,
probably start a
like,
fire. 'Cause
That's
it's-
the
Yeah,
great
these
thing about
actually use
laser
printer
printers.
drivers.
Yeah, these,
So it's the squirreliest thing that you're like, wait, I need a printer driver for my laser cutter? I'm like, okay. And just because they're being lazy and using like the simplest commodity sort of interface, they could.
so anyway, a lot of things can be really easily prototyped if you can think of a good way to make them out of a bunch of 2D sheets.
Some people even do like 2D sheets
And
that
stack
they arrange.
them.
into
Yeah,
3D
and this is
objects
built,
to make
right,
a
if you
shape.
look, the sides of this are 2D sheets, the bolt of these 2D sheets, these 2D sheets are inserted.
I've seen one out of
You've probably seen things like this, like those dinosaur pterodactyl things, those kits, that's all just
Yeah, the
2D
multiple
sheets.
kits, yeah.
All right, so 3D printers. I guess the eventual goal of 3D printers, or at least the people stage, is like the Star Trek replicator, where you make your cup and your tea in the cup somehow. But no one's anywhere near that.
We're getting close to having multicolor 3D printers, where they have different colored head nozzles, so you have full color prints.
There's one on the market now. that
I'd have to see what glaring limitations it has, but.
But yeah, I mean, 3D print, like, the 3D printing idea is such that, so the reason, so it's called additive manufacturing, and the reason for that is that most traditional manufacturing techniques start with a block and then they sculpt something out of the block. Whereas with 3D printers, you're basically adding material in order to make your shape. And what's neat about that is you can machine things and create things in ways that are impossible to do with traditional machines. Like you can make a ball, for example,
Well,
without any hole.
actually, one of the demos for a metal sintering rapid prototyper, which is similar except it uses a metal powder instead of plastic,
So it makes
is printing a ball within a ball, and both of the balls are completely solid. And apparently airport security gets really confused when they can shake something and they're like, what's inside there? And you're like, it's a ball, and they're like, open it, and you're like, it is physically impossible to do that.
So yeah, that's one thing that's cool about it. Another is that, we're getting to the point where these are probably 10 years away from being in a lot of people's homes. It's very much like the early 80s with computers, that prices are
In
ridiculous.
10
probably
years, you'll print
ridiculous.
your own spatulas.
Yeah.
Have spatula of the week. Spatula City will
We'll definitely be able to do it. How well those specialists will work is the question.
Well, we'll get there.
So, yeah.
So yeah, so even 2 years ago, we weren't talking about this hardly at all. We had like one slide on this. Now we have
We have one.
Yeah, there's one right here.
So there's desktop, so in terms of desktop 3D printers, if you want to Google these names, there's the Solid Visual, MakerBot, Replicator, Cubes, and CubeX. CubeX is the multi-program I was talking about.
And this is
Generally-
one of those. This is the solid.
Yeah, so there's Z-axis resolution right now. So the X-Y axis resolution doesn't seem to matter too much in terms of getting the final detail of the print. But the Z-axis resolution is just how tightly, how fine the slices are. And with these printers, inevitably you do see this little step pattern when you pull out a part. You can do stuff like you can etch it a little bit with acetone. Nail polish remover basically works fine. But you don't have that smoothness right when it comes out. There's also a type of printing called stereotypography, which uses a laser, and yeah, Brian was talking about
Yeah,
it earlier.
so this
And
is
there
stereo
one
laser
desktop printer
acrylic,
now that is-
where they're basically using a DLP projector, and they've got a vat of fluid. When they shine the very bright light on it, wherever the light hits, that fluid becomes solid, and then they lower the bed ever so slightly, and just keep doing this, and lowering, and they build the thing out of this goo or powder. The powder is sintering instead of acrylate, but it's basically the same idea. These are usually much finer resolution because we can get very fine projectors, and when you're moving, so like if you were doing jewelry castings, you use this because you're making something very small. You want the high resolution, and it's okay if your part that's very small takes 3 hours to print because it has incredible resolution. And then you have this thing that's printed, they do a lost wax casting with it basically, and then they give you what you
So these SLA machines, we've only put one down there because these are the desktop machines, like the ones that you could buy and have
Oh, yeah.
yourself. The Opjet and probably the one in the Meki machine shop are part of this class. So another interesting thing is that even though you may not be able to afford a stereolithography printer, once again, people on the internet are more than happy to print your parts for some amount of
Yeah.
money. So there's a company
Yeah,
called
these are-
Shapeways, for example,
Yeah,
that we're gonna get to in a second.
like those are like laptop costs, or like monitors, video game system costs, whereas the SLA stuff is still in-house costs.
I mean, this one is 2,400, and I think those are.
Well, the desktop ones. I'm
So
saying-
the one that's
Oh,
not,
yeah,
yeah, that's magic.
And there are probably 35 of these things on various Kickstarters. And they all kind of look the same, and they all are kind of promising that they're gonna somehow turn this $300 kilogram material into a $3 kilogram material. So that's wonderful, let us know when that happens.
All right, so where do you find a 3D printer? I'm sticking that in the REL, and I'll put instructions up for how to use it, and people can come in and use it. It's prone to breaking, so it's open on a trial basis. Don't count on it, but it will be there. Maybe we'll even train a TA, have somebody
Yeah,
around to help you.
so when it comes to the time where we say, okay, now it's time to see your housing, if you say, well, I designed it, but the printer was busy,
That's
we're
not
not
an
gonna,
excuse.
it's not a very good excuse.
If you want to use it, like schedule it a week in advance or something.
Yeah, figure out how to get it. Now, you might have housing and say, well, this is my housing, I want to do one more print to fix these 3 problems. That's more okay. But you can't just say, oh, I have the files, clearly that means I'm done, right? It's like, no. Have you seen how finicky these machines are? You have to actually
You're
have.
about to see how finicky these machines are.
So-
The results.
So departments have them. If you're an SCS graduate student, staff, or faculty, you now have free access to a 3D printer.
And I think if you beg, if you're an undergrad in SCS, you can probably beg for it.
Yeah, but
You
we
may be able to
can't
get
just
training.
open the floodgates and let everyone use it, but we can let people use Tom's for Solid Doodle. Design department has all kinds of fun toys. Meki has them. Everyone sort of has their secret machine that no one's allowed to use. So if you have access to one of those, they're probably way better than Tom's Solid Doodle. But if you don't, this is totally as good as the 3D printer I was using 10, 12 years ago. So, hey, why not? There's also a tech shop, which is basically an open access member, you pay for membership. There's one opening in Pittsburgh, it's gonna be at Bakery Square. There's even a free shuttle for CMU people from Bakery Square to the UC turnaround.
Yep, so basically you either pay them monthly fees to use their shop, or you can also sign up for classes on specific things, like, oh, I want to use a laser cutter, let me sign up for the 1-hour laser cutter workshop, or something like that.
So this is gonna be really cool, but It's opening March 2nd, and by March 2nd, they were totally promising like December, it used to be promising October, so like, don't plan on this.
They've announced March.
The soft
March now.
opening is
Yeah.
March 2nd.
Yeah.
So
They've announced March.
things will probably not be ready.
If you were interested in some of the things we've discussed here that we have not covered in enough detail for you to do, a tech shop is a great place possibly in the near future for you to go and learn about those specific things. And they'll also have a range of these machines, like they have mills and lathes and a couple of 3D printers and laser cutters, so you can see all of that stuff in one place.
Hack Pittsburgh is like the non-profit version of Tech Shop. It's been around longer. I think they have fewer machines. I'm not even sure that they have a 3D printer. Like one of their meetings, it was like budget for 3D printer. Like that's one of their notes. That was last fall. So maybe they have one now, maybe not. But
Yeah, they
check them out.
also-
They're not that far away either.
They're also, I think they're uptown or something
Yeah,
like that. And basically, they also have free open houses every Friday, and they have the same sort of sessions where people can come in and do stuff, although they tend to integrate a lot of friend stuff like basket weaving and things. So if you're into
So
that-
if you're not part of the secret clubs, these are some very nice options that are out there. You get to meet other people who like this stuff. Probably could be worse.
Okay, so random calls.
So in the meantime, we can probably
There's all
start
kinds of
getting into
details, but I think having one here is probably,
Once you see these parts, all of a sudden, a lot
Let
of
me check
things.
the temperature first.
So the first thing is
I can
that
touch it, so.
these,
That's not how you should check
yeah,
the temperature.
don't do that.
There's these
Yeah, I have
things,
special hot.
there's a monitor that says, temperature of these things. 47 degrees Celsius is probably okay. But I'm gonna move the Z-axis down.
Let me get out of the way, see how fast it's going. Because that's, it has a very fine resolution, it's not really meant for speed.
I have burned myself on the hot end, the part that shoots the plastic.
And this is something where if there were 5 of you who wanted to do a print job and it was 8 o'clock at night, we would recommend you put all 5 of your parts on the bed, maybe notice how small the bed is. And then if you're lucky, all 5 of them will print and they'll be ready in the morning at noon.
And that's,
So, or you have to baby it all night and like print one after another because the machine isn't being used from 2 a.m. to 8 a.m. You sort of lost 6 hours of printing time. So I would, when I was printing lots of stuff, I would always make sure I had like a 24 or 25 hour job so that the entire job was printed. I didn't have to come in at 7 o'clock at night or 9 o'clock at night just to swap print jobs.
well, this one almost fits. Yeah, it fits.
All right,
Snapped
so
up. Look at that.
there you go. So we'll pass
That
that around.
was the one that was on its back.
It's amazing.
And this is the one that is on its side, and you can sort of see, actually, one of the things on my slide
Does anyone else have a mini gadget?
overhangs,
Snap on.
that one. Like,
The overhang is,
So we got 50% yield
Yeah.
trying our random fiddling with Tom's Solidoodle. That's basically how the Solidoodle is going to work. That's how a lot of the FDM machines that are really, really cheap work, is you print out a thing, it doesn't work, you figure out how and tweak it,
Yeah.
and then you try it again.
and just something, you look at this and it looks pretty good except for these corners. So what I would do if I was doing this again is I would iterate it and try to round off all those top corners so that the light was nice and even. And you could just keep playing with it because, right, this only took, it took twice as long because we printed 2 of them, but,
yes.
But we also didn't have to be doing anything while I was printing, you just have to be around.
Yeah. So, yeah, small parts actually are a little harder to print. Small features, like a hole for a screw might be hard. But what you can do is you can make it a case, put in a piece of plastic where you plan to screw something in, and then drill that with a regular drill.
yeah. Yeah, there's nothing stopping you from using an X-Acto knife.
You can sand it, make it
Sandpaper.
smoother.
You can do whatever you want with this thing, and then
You can paint it.
you've got close to what you want. And maybe that's good enough.
At the end of the day, you end up with a piece of plastic. You can do anything that a piece of plastic can do.
And how much is this stuff a pound? It's like $10.
$25.
So at the outrageous, small business markup, Tom pays $25 a pound for this plastic, but a pound of that plastic
It's a lot.
is a lot of little parts. So, that's, we're probably not gonna bill you unless you start trying to build like giant life-size things out of lots of little pieces.
Okay, so 3D printing resources online, if you don't want to use the Solidoodle or anything, and you want to be guaranteed that a part will work, Shapeways is a good one. They basically have tons of 3D printers and just design and they will print it for you.
Yeah, and they do different
it's-
materials
and it's-
now as well.
Right, and it's a marketplace, so you can just, people will post stuff and then you can print it from them and that person will get some royalty. Kind of like t-shirts on Cafe Press.
Yep. So they do a number of materials. They do plastics, metals, and I think the newest stuff is ceramics. So you can actually print stuff like custom.
That cup, space cup.
Yeah, space
I
cup.
kind of want that.
They're washable, but not dishwashable, I believe, is the state of the art in ceramic printing. But yeah, if you want to make like really cool jewelry and all sorts of stuff.
So,
Yeah, there are people who design stuff specifically for 3D printing to make things that are just impossible
Yeah,
to make.
so it's a little, well, it's a fair bit more expensive than Comp Solid Doodle, because they have to.
But
print
much
out
more
fancy
reliable.
picture. But yes, that you can be guaranteed that at the very least your art will print out the way that you designed it, which may or may not be the way that you wanted it.
So for Gadget 1, I wouldn't worry too much about this stuff, but Gadget 2 is basically, we'll have a theme, but if you have a better idea, we're generally fine with doing whatever you want for Gadget 2, with a few constraints. And, you can basically look into whatever you want to make with it. If it's a little bit of electronics surrounded by a very cool shell, that's fine with us.
Then if you have a 3D printer, for example, and you want to make
Sign
random
up for
stuff,
that one.
there's a site called Thingiverse which just has tons of free designs. So if you want,
So for Gadget 2,
Star
if
Trek
you want to,
indicator
when's the
that-
deadline on this 3 chances to win thing? Because
Yeah.
for Gadget 2, you can
Fine.
submit to the MakerBot example thing. Can we go back? I actually want to see if that deadline is
No.
passed.
Which-
Go to the MakerBot page.
Wait.
Yeah.
Okay.
When's the deadline on this 3 chances to win the thing? March 8th. Damn. Oh well. Maybe some of you can submit your gadget plans.
Okay, so back to the slide. So this is 3D printing. Now, maybe I think we dial it back a little after showing you all this crazy stuff.
Yeah. All right.
You don't have to do all that. If you've made a Halloween costume before, if you made anything like out of construction paper, poster board, like that's okay too. We're not trying to make you like go use 3D printers and laser cutters. We just want you to be aware that they're getting way easier. Like 10 years ago, we wouldn't have those slides. Now we're sort of saying like, here you go. So like if you've made anything since you've been 8 years old, you sort of are equipped to make some very nice gadget stuff. Right? You can be whimsical. You can have a lot of fun with this stuff. And there's all these details where you're sweating over making your housing. You spent hours learning some crazy new CAD software and like getting SolidWorks to make the lofted shape design that has to be perfect, right? And you then spent 2 weeks and then you had like a machinist make it, or you had like Shapeways make it. Or you went down to the CMU art store, which has a lot of great stuff, and you bought some nice poster board. You bought 3 colors of poster board, all that. You bought the nicest X-Acto knife they have, a brand new bottle of CA glue, and then you like put it together nicely. Like you might end up with something nicer, right? Because this is subjective. What's nicer, and where is your time better spent? Is it better spent? Where do you want to put your effort in?
The only thing you want to be concerned with is you want to make sure you've planned it out. Like you're going to be laying out your circuit board, so just at least think about where things go, which things are on the board, which things are on the board.
Yes.
So regardless of how you construct the housing, you still have to think about what the housing actually looks like, does, and what user interface.
And that is how we are going to grade your housing based on, you're going to tell us what your housing is going to do, and then we're going to grade you on how well it does what you told us you were going to do with it, and also, did you include everything that you were supposed to do?
So just some materials to think about, yarn or fabric or silk. There's even conductive thread, so you can sew thread right into fabric. Balsa, CA glue, cardboard, pine.
Yes, I think this thing, if you go up near it, there's an IR sensor somewhere, don't ask me where, and then it sees you, it turns its head towards you, and then does a bunch of chomping, and then it looks away. Right, because it has servos inside to turn, it's got IR to see you, and it's got a motor to bite. Right, and it's great, and it does exactly what it's supposed to do. I'm not sure this would be any cooler if this was like a stainless steel thing with like razor sharp teeth. Might be a lot.
You want to talk about shape lock?
Shape lock. I think it's actually L-O-K. I don't actually know. Just Google shape lock. If you've ever played a sport where you had to like get the mouth guard that you boil in water and then you bite on it, that's sort of these thermostat plastics. You can also just buy like great chunks of it where you kind of heat it for a while and then it kind of stays like silly putty consistency. Then you can like shape it into various things. And then eventually after, once it cools down, it's actually kind of hard. So you kind of get this cool custom plastic thing, but you got to just shape it with your hands.
The plastic ends up being sort of similar to what the Finch's plastic.
Yeah, so it feels like that shell.
End of the process.
So you could like design your board, you could have like a couple things and like just stick your sensor right in the goofy plastic, the plastic, because you can kind of just poke at it like it's a putty. Build your thing out of putty, but then the putty becomes plastic. So it's kind of cool. It's not that expensive, but you want to order it ahead of time if you want to play it, but I don't have any on hand.
Yeah, but I think there's also Super, which is the silicone rubber version of that, where it's the same thing except it doesn't harden completely. It basically becomes a soft rubbery thing in whatever shape.
So if you want to use this class as an excuse to play with crazy materials, 3D printers, shape lock, dinosaurs made out of cardboard. And then there's a couple places, like the CMU Art Store is surprisingly good for this kind of stuff, because the design department does architecture, they do a few things about making things. I think Utrecht is still in the south side. There's a mysterious art store at Hobart Whiteman, I haven't been there, but it's there. Tower Hobbies is online, Hobby Lobby. I think there actually is one in Robinson. Yeah, but they have surprisingly cheap carbon fiber. Should you ever find a need for carbon fiber, lots of other places charge 10 times as much.
Okay, so we will eventually give you a gadget housing assignment. We're not assigning it now, but this lecture is here because of your circuit board design coming up. So, but just know every gadget is getting a housing. That will be a requirement. And you'll build it with whatever materials you want to make it out of. It's probably going to be due about a week after spring break. So once you have your gadget, you will need to enclose it. Like you'll build your gadget and then you'll make your housing. And then you'll give it to users and they will tell you whether it makes sense. Great. So think about it now. And that is it for now. We're extending the deadline for the Gadget 1 schematic. And on Wednesday, we're actually going to go through like a live demo. We are going to make a Gadget 1 example in Eagle. We are going to criticize our own example, and then we're going to make the layout, criticize that. We're going to do the DFM part.
Because, right, Eagle, I'm sure, how many people are enjoying working with Eagle? Eagle is a little confusing, and maybe you're not, if you're having trouble figuring out how we're going from like design of a gadget to a schematic to the layout and how it's all working together, we're just going to do it for some gadget that we want, and then we're going to make it. Maybe we'll throw it on the panel. I still need that LED controller.
So in any case, the schematic part of Gadget 1 is not due on Wednesday. We're deciding what will be due, but definitely not Wednesday.
Does not hurt to think about it and try to do as much as you can ahead of time.
Of course.
That's what Will said.
So any questions about the class generally before we if you have questions about specific stuff, we'll stay after.
If you have the plastic bits, you bring them back.
It's so funny.
Is that right?
It's crazy. Talks about it. I know.
It just sticks.
But it's really funny.
They're really cool. And they're funny. And they're really clever, but they're not like they're really big baby sticks. They're not like.
The way he talks about it is so funny.
This whole I think I just kicked your camera.
You're on camera. What?
See you, Joey.
What happened now? I think it was yeah, usually
It's supposed to be an opening of a door. And so like rain and stuff is the biggest issue. It's not what I'm saying. Water, like
What was the 5 bar? You're hammered. Wait, how long were you Yeah, kind of. Well, like we had been at Kiddo Bar beforehand, and then like they had last call and kicked everyone out. So we went to 5 for like a drink, and then they had last call and kicked everyone out.
There are no passion makes it. For some reason.
Expensive driving.
That's probably what I've seen on the roads. Have you seen the stuff this guy named Theo Jensen makes? Theo Jensen. He's the guy who makes the weird little like walking creatures.
I mean, I would say we get
It's so funny. This was neat. Yeah, I've seen that one. It's super
whether
fun.
that should
I love that he builds like big 10-foot tall ones and just sets them loose on beaches.
Yeah, I was fun.
Yeah,
I've seen that.
they're wind powered. They just walk around. Rolls are canceled this weekend.
Seriously?
Yeah, they don't have permits.
Seriously?
Yeah, seriously.
I just sent out an email saying, hey guys, weather looks good, we're gonna have rolls.
No, too soon, Glenn. The weather looks iffy. From what I've seen, but yeah, rolls are canceled because they don't have permits because LOL, Josh Hickson.
As a fucking terrible sweepstakes.
Well, this is out of their control because they probably, I mean, sometimes there are things that happen in Shannon they can't get permits around. But it'd be nice if they got emails. Like as is, we're gonna have one weekend of rolls before spring break, right?
This is just awful.
It's kind of silly.
It's
I might miss it because I'm going off to see a concert that weekend with some friends. Now, I could probably make some plans.
why
Yeah,
did
they
work
can't
on
do it this week. Well, they can't get permits this week. They had the permits for the last 2. They got canceled because they weren't. Well, 1, the weather wasn't good. 2, there were no hay bales or road signs or
most
anything
of those things
really.
are under their control.
Yeah.
Well, I guess I have time to do my stress analysis project.
But nobody voted for Julian Kessler because you don't want an SDC person to be in charge. There's nothing worse than that, right? God forbid we elect someone competent.
Yeah, he's kind of a douchebag. That's what I hear. I haven't met him personally. But I think that's the party line.
No, it was definitely a party thing. The whole election was basically rigged, which I'm now narrating on the camera for all to hear. That's right. You heard it here. Sweepstakes is a sham. It's all rigged.
About that.
Connor Hayes, our inside man.
Connor Hayes, our let's create buggy secrets to everybody.
Yes. Absolutely true. Declassifying sensitive information. Immediately.
You can make it more complicated. Psychiatric
Potentially making things up.
don't get to talk to
I don't know either.
Gotcha. Already smaller, top of
Screech grain of salt status.
Grain of salt.
Take a grain of salt, maybe. I don't know.
Rolls canceled.
Well, rolls canceled. That's something you have to accept.
You know what we could do? We could roll on your car.
Peace out. I witness camera.
I'd almost be willing to bet that folks are just going to work it out because you need 3 volts at least.
So, probably red.
Yeah, so, but that's the speed.
Well, it's mostly with people ones, and I was curious how the rating system, I guess I noticed you're iterating through, you've got one color that's going up, one that's going down, the other one's off. Yeah. And so I guess the idea there is you're sort of saying red to green, green to blue, and then blue to red. Okay.
And then it should, the other thing that's noticeable is like it starts on red and stops on red. That's what the loop looks for, whether it should go back to
It doesn't show.
Just doesn't check every single millisecond. So it should always be red when you like.
Your batteries.
Your battery's almost done. Okay.
So,
I guess it was running that whole time. Alright. And I haven't charged it once actually since getting it, so that makes sense. So all my testing has been on the same battery without ever charging it, except for the first time that I turned it on.
And then I guess I was also curious, so the way the timing works, I guess you have,
do you need to shut this down?